All right, this video on related rates is going to go over two examples of how we can use implicit differentiation to work on applied problems. So let's say that we have a balloon, it's being filled maybe with a machine, so there's a constant rate of flow of 2 cubic centimeters per second. Now I want us to think about, there's a word rate here, and then I want us to think about the units. This is a volume unit over a time unit. So the volume inside the balloon is changing at a rate of 2 cubic centimeters every second. That's the rate at which the balloon is being blown up. How fast is the radius increasing when the radius is 3 centimeters? Now, one thing I want you to think about is when the balloon is smaller, 2 cubic centimeters per second is going to blow up the balloon. It's going to seem like it blows up the balloon a little bit faster because there's just not as much space for that air to go in. But as the balloon gets bigger, there's more space for that 2 cubic centimeters to be in, so the radius isn't going to grow as quickly as the balloon fills up. Now you do need to know in this one that volume of a sphere is 4/3 pi r cubed. And then I'm taking the derivative with respect to time, not respect to the radius. So v prime of t is 4/3 pi times 3r squared, and then I'm taking the derivative of radius with respect to time, so dr dt. Now another way to write v prime of t is dv dt. Those are the same things. And now I'm going to plug in and solve. So I know that dv dt, change in velocity, or change in volume, excuse me, over time is 2. I'm going to cancel those two 3's and write that this is 4 pi. I'm looking at the radius being 3 centimeters. I want to know how quickly the radius is changing at that time. Well, I'm going to write that this is 2 over 12 pi, or 1 over 6 pi, and that's going to be in centimeters per second. If you wanted to plug that into a calculator to find the exact answer, or to find the rounded answer, you can, or you can leave it in exact. All right, let's look at one with some trig in it. A rocket is launched, so it rises vertically. There's a camera that is positioned 5,000 feet away. Now that is always true, okay? It's always there. However, the height is going to be changing with respect to time as the rocket goes up. At the moment when the rocket is 1,000 feet, its velocity is 6,000 feet per second. Find the necessary rate of change of the camera's angle as a function of time so that it can stay focused on the rocket. So as the rocket is increasing, notice that your camera angle is going to have to move up that way, right? And so let's use a trig function. I'm going to use tangent because I know opposite, I know adjacent. So I'm going to say that the tangent of theta is equal to h over, now my adjacent stays 5,000 no matter what, okay? All right, let's take the derivative with respect to time. So this is going to be secant squared theta. Theta is a variable. It changes with respect to time, so I need to write d theta dt. And then I can also write this as 1 over 5,000 h. I think that's helpful, because then I just get 1 over 5,000, but I took the derivative of h with respect to time. Okay, I'm solving this for d theta dt at the time when h is 1,000. I also know the velocity, the change in height with respect to time, is 600. let's think about what secant of theta would be if I know h is 1,000. Well, secant is 1 over cosine, so I'm going to need to figure out the hypotenuse here. 5,000 squared plus 1,000 squared and square root. Okay, and that is 5099. So let's look at what the secant then would be. So cosine of that theta angle would be adjacent over hypotenuse. So secant would be the reciprocal of that. And then I need to square it. All right, so let's go ahead and plug that information in. So I get 5099 over, oops, that should be 5,000. I'm solving this for d theta dt. And dh dt is 600. Okay. I could write this in the most exact form possible. I mean, I already kind of rounded to get the 5,099, but that's okay. So I would have 3 over 25, and then I would just multiply by this reciprocal. And that would be the rate of change with respect to time. Let's go ahead and find that this time. And I'm using a TI, so I went up and pulled this exact answer. So if you get a little bit different from me, then that's okay. So 0.12, and that's going to be radians per second. That's my rate.